Welcome to lecture number 7 of Probabilistic Machine Learning. Here we are in the course. In the first 6 lectures, we saw that probabilistic reasoning is an extension of propositional logic that allows us to reason with uncertain statements. We saw, lecture 2, that doing so poses new computational challenges because we now have to keep track of an exponentially large, potentially exponentially large set of hypotheses. In lecture 3, we saw that we can even extend these probabilities to continuous spaces, which in a way complicates the computational issue even further. So in lecture 4, we got to encounter our first computational tools that provide actual methods to do inference in even continuous valued general probabilistic models. These are called Monte Carlo methods, and we used them, extended them in lecture 5 through a relatively generic toolset. In the last lecture, the most recent one, I introduced another crucial tool for probabilistic inference, which is given by Gaussian distributions. Gaussian distributions, as we saw back then, map probabilistic inference onto linear algebra. And linear algebra is something that computers are good at, so therefore they're going to be a beautiful tool to use. Gaussians don't just, what I mean by mapping inference onto linear algebra is not just one single property of Gaussians, it's a whole list of such properties. Products of Gaussian probability density functions are given by up to normalization, another Gaussian probability density function, where the parameters of this distribution are given by, can be derived from the parameters of the inputs for the product using operations that amount to linear algebra, inverting matrices essentially and multiplying matrices and vectors. Marginals of Gaussian distributions are Gaussian distributions. And that's convenient in particular because the marginalization operation is very straightforward. It amounts to just selecting subsets from a vector and a matrix. Therefore, this operation provides an implementation of the sum rule in the Gaussian family. Linear conditionals of Gaussians are Gaussians. That means that if a Gaussian random variable is mapped through a linear map, then first of all, we get out another Gaussian distribution where the parameters of the distribution are just mapped either from one or from both sides through the linear map in question. And therefore also we can show that conditionals of Gaussian distributions, so that means given an observation that is related to the quantity we care about in a jointly Gaussian linear fashion, the posterior distribution essentially, or the conditional distribution arising from this kind of observation, is also Gaussian. And because this provides the product rule and this the sum rule of probability theory essentially, we can also construct Bayes' theorem and see that if all the variables in question are jointly Gaussian distributed and all the observations we make of them are linear projections of them, then posterior distributions of these quantities and all their linear maps are also Gaussian distributed. The corresponding expressions can sometimes be a little bit tedious and you have to stare at them for a while to see the structure in them. But so far the most important takeaway was that all of the operations you see in here are just linear algebra. They're just products of matrices and the solutions to linear systems of equations. So that amounts to, in simple terms, inverting matrices. What we're going to do today is to use this insight to construct our first concrete, still very basic, but concrete Bayesian machine learning algorithms that allow inference on non-trivial quantities that are actually important in practice. I will still start with a very simple example, of course, and this will very quickly evolve into a much more complicated framework, or much more powerful framework as well. And in the process, we will actually have to look at these expressions a few more times, a little bit more in detail, but we'll do so deliberately, very slowly, so that you get to see what's actually happening on the computer. So what is the problem we're going to solve? It's the problem of learning a function, or in fact inferring a function. In probabilistic reasoning, the words learning and inference are often used interchangeably, even though other parts of the machine learning community don't do so. We will see over the course of this lecture why this might be the case. The problem we're going to start with is trying to figure out a function that explains this kind of data set. So here we have an input, x. In this case, we assume x is a real number, but very quickly we will move to examples where x can be a vector in a real vector space. And this x maps to some other quantity which we get to observe with noise. So we're going to collect pairs of x and y, like these little crosses in this plot. And then the question, of course, that arises is, if I give you new x, can you predict new y's? What this amounts to is to say, there is some functional relationship between x and y. And what I'd like to know is this functional relationship. This problem, of course, is known as supervised machine learning, where we get inputs and targets, x's and y's. Now, this is a particularly simple data set, maybe. And so normally in a lecture, I'd like to ask you now, why is it a simple data set? But this is one of these questions where students often find it too easy and then don't even dare answer because they fear that they might look like a fool. So, of course, the important aspect of this particular data set is that it's quite well described, maybe, by an underlying linear relationship, by a straight line. Don't worry, we'll quickly talk, very quickly talk about functions that aren't linear. But this is still an interesting case, right? So where does this arise? So you might think that this is too trivial a problem, but it's actually not entirely impractical. So here is my former wonderful colleague, Jeanette Bock, when she was still working in Tübingen with this robot. It's called Apollo. She's now working in Stanford, but the robot is actually still here in Tübingen. And so robots are complicated machines, and doing something interesting with them requires expert knowledge. But there are also some low-level tasks in robotics that are quite easy, which I'm going to use as an example for, well, easy. They have quite simple structure, which is something I'd like to use as a motivation for this data set. So let's say you've just bought a new robot, and one of the first questions you might ask while you're setting it up and testing it out is, if I send a certain amount of current through one of the motors that activates the joints, like one of the joints of the robot, so let's say, I don't know, maybe the motor, the electrical motor in here that twists this arm, then you can imagine that if you increase the current, then the force applied onto this arm increases, probably relatively linearly with the current. And if you lower the current, the force goes down, and if you run the current in the other direction, so in the negative direction, wherever that's pointing, then the arm is trying to turn in the other direction, and the force applied onto that arm will increase linearly as well. So what you might do to figure out the relationship between these two is a measurement like this. So you basically apply some kind of force measurement device to the arm, and then you activate just this one joint, and you run through various different settings. X might here be the current going in. It can flow either in one direction or in the other. And what you're measuring here is the force that is produced at the arm. You do a bunch of measurements like this, and of course, because you're a good scientist, you know that your measurements are imprecise. The machine that measures this force is maybe not so good. Maybe the whole geometrical setup for the robot is not so great, so there's quite a lot of measurement noise here. With apologies to all mechanical engineers looking at this, I'm sure in practice everything's much more complicated. It's just a motivational example, right? So what you might want to know is what the linear function is that goes through this kind of data. What is a linear function? Well, a linear function, yeah, okay, so here's the question again. Maybe we can think about this briefly in terms of variables. So we have our input x, we have our output y, there's a functional relationship between them. Notice that we get to see both. That's why it's a supervised learning problem. The only thing we don't know is the function in between, this latent function. Now, of course, there are many possible functions, right? There's the space of all functions that map from x to y is incredibly large. So what we're going to do is something extremely restrictive. We're going to assume that this function can actually be described by just exactly two numbers. Those two numbers are given by the intercept and the gain of this linear function. So we will assume f of x is given by one number, which we don't know yet, plus another number we don't know yet, times x. So that's clearly a linear function. W1 is called the intercept, so W1 is the value of f at 0, right? And W2 is the gain, so that's the slope of this linear function that we're looking for. One particularly convenient way to write this function, which we're going to use a lot, is this one. I'm going to briefly talk about the notation in a bit more detail in a moment, which uses a function which I'll call phi short for features, and this is a function that takes in an input and it returns a function or several possible functions of that input. In our case, this function just returns, first of all, the constant 1, and secondly, x. So this seems like a trivial function, but it simplifies this notation because it allows us to write the function f of x as a linear map, not just of x, but also of the vector of these unknown numbers w1 and w2. So our learning problem now looks like this. Here's a graphical model, a directed graph. What's happening is we take our x, that's the input, and then we compute these features phi of x. In this case, the features are just 1 and x. Now we have decided that we're going to do this, so we know what these features are. There's nothing uncertain about them for us, because we claim to know that this function is linear. The only thing we don't know is the intercept, that's the weight on the first feature, and the gain, that's the weight on the second feature. Now what we'd like to do is learn or infer these two quantities, w1 and w2. And they are related, of course, to the data, to the output in a linear fashion. So we could, of course, assign a generic prior distribution over this bivariate real vector space spanned by w1 and w2. And then we could assume any kind of likelihood function that connects the function f of x to the observations y, and do Bayesian inference. That's the generic framework. However, if we don't choose the prior and or the likelihood in a convenient way, then this inference will in general be quite expensive. We will get a generic distribution, posterior distribution over w1 and w2, and it can be quite hard to compute this posterior because it involves a complicated integral for the normalization constant and so on. So to simplify our task, because let's be honest, this is a very simple task, so we can't afford to run some super complicated, powerful supercomputer on it, we will decide to make very strong simplifying assumptions, which is that we will use Gaussian distributions to describe the prior on our model and the likelihood. And now, because there is a linear relationship between the thing we care about, the w's, and the stuff that we get to see, the noisy version of f, the posterior is going to be Gaussian as well. So let's see if we get this to work. So we will put a Gaussian prior on the weights. Here is such a Gaussian prior. I've decided to use a particularly simple Gaussian prior. So here is our bivariate space of quantities we don't know yet, w1 and w2. I've decided to put a Gaussian prior distribution over these w. This is a bivariate distribution that involves a mean, that's a vector of length 2, that's this dot here in the middle, this circular dot down here. And I have also put a covariance matrix around this distribution that's described by this matrix sigma. And it's sort of shown both as like the PDF arising from this is given as a shading in green in the background. And these circles here are equipotential lines of the Gaussian at 1 and 2 standard deviations away from the mean. Now you can guess what I've chosen here as a sigma. It's the unit matrix. So this is a standard Gaussian. It's just because I couldn't really think of anything else for the moment. Let's see if it does something interesting. And then of course we can change it later on. What I'm also showing are 3 random numbers drawn from this Gaussian distribution. These are these green dots. Okay, I'm deliberately going very slowly. You can also stop the video if you want to at any point, because we are very quickly going to ramp up this process to much more complicated models, and it's good to think about it in this very basic fashion now. So this prior distribution on the weights of this function actually also imply a Gaussian prior distribution on the values of the function. And the reason for that is that the function we care about, f, is a linear function of, and here is an important point, a linear function of the weights. So this function here happens to be a linear function in x, but what's actually more important is that f is a linear map of the weights. So here is some function phi that is applied to the weight vector w. So because of this Gaussian distribution over the variable w implies a Gaussian distribution over a joint Gaussian distribution over all the function values that f can take anywhere. And I'm showing you this plot here. So, well, I'm showing you these function values in this plot here. So here you see a map from x to f of x. And what you are seeing in this plot, I'm again going to go slow because I'm going to use these plots a lot, are many different things. So first of all, this mean in here, this green dot at 0, 0, which I've chosen to be 0, 0, corresponds to a mean for all the function values. So at any location x, the mean prediction for the function value f of x is just phi of x times mu. So mu here is 0, and therefore the mean of the function values is going to be 0 everywhere. And I show this as a solid green line in this plot. Secondly, this covariance over the weight space applies a covariance between function values. Now what this means here is that if you take any 2 function values from anywhere in here, so let's say we take 2 and minus 4, then the covariance between the function value at location 2 and at minus 4 is the inner product taken between the feature vectors of 2 and minus 4. So that feature vector is 1 and 2 and 1 and minus 4. We apply it from the left and the right to this covariance matrix here. And because this feature function involves x, what we get out actually depends on x. And you can see the diagonal entries of this variance matrices shown, of these covariance matrices shown by this green kind of sausage of uncertainty around the mean value. And notice that it gets smaller as we get to the origin and gets larger as we move away. Why is that the case? Well, at 0, the entry for the variance of the function value at 0 is just, actually let me write this out. The covariance between the function value at x and the function value at x prime, for any 2x and x prime, is given by the feature of x. I'm going to use this simplifying notation, transposed times sigma times phi of x prime. So what is phi x? Phi of x is the vector 1 and x transposed with this matrix. In this case, I've actually chosen this to be the unit matrix. Let me write it out like this. And then we apply from the right hand side 1 and x prime. So if we choose particular values for x and x prime, and let's say this is the unit matrix, then we're going to get sigma 1, 1, or actually let's just keep the sigmas. Sigma 1, 1 plus sigma 1, 2 times x prime plus x times sigma 2, 1 plus x sigma 2, 2 x prime. So in particular, at 0, if x is 0, so if x and x prime are both 0, then we get the variance of the function value at location x, or 0. Then all of this is 0, and we just get sigma 1, 1, which happens to be 1. So that's this value here. If we are at 6, then we get 1 plus 6 plus 6 plus 36. That's the variance. I'm plotting here, of course, not the variance, but the standard deviation. That's the square root of the variance, because that has the right quantities, the right units of measure. And you can see it that it's sort of on the order of the square root of, well, whatever that is, right? So 1 plus 12 plus 36. Okay, I'm also showing in blue in here the values of these feature functions phi. So there's a constant function here in blue, there is just 1 everywhere, and then there's this linear function that is just x. And then finally, every single sample in the weight space corresponds to a value or to a particular function in this hypothesis space over functions. So let's see if we can get these out. So this is maybe a good point where you want to stop the video and think about which function of these three that I'm actually, so I can tell you that these 3 green lines in here, they correspond directly to functions associated with these samples. Now you might want to stop the video, look at these 3 green dots, and think about which of them corresponds to which straight green line. If you've done that now, let's do it together and check whether you were right. So here is one function that is, it's close to the origin and it's just above the origin, which means that its intercept is 0, it goes basically through 0, and its slope is positive. That's this line, right? So it goes almost through 0 and has a small slope. Here is a function that goes, has also a small intercept, it's just below the origin, and it has a steep slope. That's this function. And then here is a function that has a negative intercept, so it goes below the origin, and it has a negative slope, so it goes down. And that's this function. Okay. So now what I'm going to do is, I'm going to use this as a tool, as a didactic tool over the next 1 or 2 or 3 lectures. Notice that actually this entire distribution is circularly symmetric around the origin on the sort of in a circular way that is described by the shape of these circles. So another way to think about this is if I took this plot and I rotated it such that these shapes would stay circles, then every single sample from this rotation is an equally good sample. Right? There is no reason to prefer this sample over one that is rotated a little bit over here. So what I'm going to do is I'm going to show you animations like this where samples, typically 3 of them, are running around on circles. And then that means every single frame of this video represents 3 equally good samples. Now, of course, each of these samples has a different probability. One of them is closer to the origin, so it's running on a circle where each point has a higher density, and some are running outside. But every single one of them across, like for each of the circles, so for each sample, every frame of the video corresponds to an equally good representation. We will do this because soon I will have to stop showing you these weights, because then we're going to have more than just 2-dimensional weights. And then I can only show you these plots in function space, and then it can be helpful to get these animations to see the sort of flexibility in the model. Okay, so if you've stared at this for a while, then you can also find the slides, by the way, of course, on Ilias. The animations are in there. You just have to use the Adobe Reader to see them. Otherwise, you don't get to see them. We can now talk about the notation a little bit again before we go to the inference. So sometimes people get confused by this, and in fact, well, not just sometimes, admittedly, it is a confusing notation, but it's extremely helpful. So let me take a few minutes to recap again what we've just done here to simplify the process of thinking about a very large number of function values and several possible weights to explain them at the same time using notation that is very much inspired by the beauty of linear algebra. So what we're going to do is we're going to learn a function that, well, we will learn a function from a data set that is given by x and y. X is a collection of inputs. There is a reason why I'm using a capital X here and not a vector x, because we're quickly going to find that the x's can really just don't necessarily have to come from a vector space. They can just be collections of x's. Y are observations. These are the outputs of the function, and we will assume that these are real numbers. So if you have a whole data set, then this data set consists of a collection of n different x's and n different y's. And now I'm going to use the following notation. I will introduce this function, which I just already did, phi, which is the feature function. This is a function that maps from the input domain, from x, to a real vector of length f, where f is the number of the features. In this first example, the number of features is 2. So there is feature number 1, feature number 2. The first feature is the unit function. The second feature is the linear function x. And instead of writing phi of x in this notation that you're typically used to for functions, I'm actually going to write phi under the subscript x. And so A, because this simplifies notation a lot, so if you have a lot of x going around everywhere, then this just makes these expressions very long. So this simplifies this a bit. You can also actually take this as slightly suggestive, as meaning that this is essentially this feature function you can think of as a very, very long vector where you could plug in any value of x, and then this particular value of x kind of indexes one location in this vector, or actually this matrix. So if you take all possible values of x on the real line, then that's an uncountably infinitely long vector. If you apply f to that, you get an uncountably infinitely long matrix of height 2, where every single first entry is 1, and every single second entry is just x. Okay? This is a little bit shady to do it this way, but actually it works really well. So good. So we can also do this for our data set. If we evaluate phi at the entire data set, then that's phi of capital X rather than low x. And that gives us an actual matrix that has size number of features by number of data points. So if we have, let's say, 20 data points, then this is a matrix of size 2 by 10, because we've decided to use 2 features, 1 and x, and there are 10 input points. So phi of capital X is going to be this. In this case, it's a sort of short and stout matrix. And then I'm also going to talk about the function value f evaluated at some x. I'm going to use the same kind of notation to simplify this and get rid of all these complicated brackets. And of course, there's also function values at all of the input points, at all of the training points. So how do we get those function values? Well, these are a vector. So we apply, by our definition of the function, phi of x transpose to the weight vectors. So here's our vector of weights, w1, w2, which we don't know yet, but we're going to infer them. And here is this matrix, phi of x, that we have up here. We've taken the transpose of it, which gives us the set of all the first features and all the second features. So these are all 1, and these are all x1, x2, x3, and so on up to xn. And if you now take the inner product of that, we get, well, the vector, matrix vector product of these expressions. Then we get a vector of function values, where at each of these entry points, we get the inner product between the feature vector of this particular location, x1, 2, 3, xi up to xn, with the weights. And these are just the function values at x1, x2, and so on up to xn. Okay. This might sound like a tedious notational exercise. You will soon see that this extremely simplifies what's going on, and I'm going to quickly start using this in a relatively unquestioning way. I'm also sometimes going to mess a little bit with the notation and use capital phis for these matrices. This just happens in between because I try to clean up my slides, but sometimes I still forget to fix some of them. Okay, So this has given us our notation that maps this description of our function f of x onto linear algebra. And that means we can now do Gaussian inference on a function given data, because the data is linearly related to the aspects of the function w which we don't know. So to do so, we just do Bayesian inference. So we write down a prior and a likelihood and then use Bayes' theorem. But because everything's Gaussian, the posterior is going to be possible to compute using linear algebra. So we start with putting down our prior. I've already done that before. This implies a prior on the function as well. It's not like the relationship between these two is just due to the properties of Gaussian distributions, because f is a linear map of the weights. Now we introduce a likelihood that says we are going to evaluate this function f of x at various points x, and we will get out noisy measurements of the function at these locations. So we're going to apply a current to the motor in our robot, and we're going to measure with a little bit of measurement noise what the force is being produced by the joint. So the likelihood, our observation likelihood, we will assume to be Gaussian. And again, this might be wrong in practice, but we're just going to assume that it's true because it simplifies our computation. And what we do when we evaluate one of these data points is we evaluate our function f. Our function f, by our assumption, is given by a linear mapping of the weights. And we assume that we have some measurement noise. So that's an error bar on the y's. And I'm actually going to assume that all these different measurements are independent of each other. So there is the covariance here is just a scalar, which I call sigma squared, times the unit matrix. Actually, this assumption is not strictly necessary. It's possible to work with a generic covariance, but it's a very typical kind of assumption that people do in practice, right? Every time I measure, I make a different kind of mistake. And the mistake I make at time t and at time t minus 1 are completely independent of each other up to the fact that they are Gaussian and have variance sigma squared. And are measurements, of course, of the underlying function. So given the function, the observations are actually independent. And if you want to go back and check out the graphical model on a few slides ago, you will notice that that's actually true by our model, this conditional independence of the observations. Now we can compute the posterior. So to do so, we multiply the prior with the likelihood. So we multiply this distribution with this likelihood, and we normalize, and we get a posterior on the weights. So to do so, we just have to multiply one Gaussian with another Gaussian, and then divide by a normalization constant, which also has Gaussian form. And we can look up what that is on previous slides that we've done in the previous lecture. So now we're going to get one of these complicated linear algebra expressions that we spoke about in the previous lecture. And maybe now is the time to actually plug in like the corresponding numbers. So if you read out what the expressions are, you can just plug in the concrete values we have in our model now and see that the posterior on the weights is going to be the prior mean. It's going to be a Gaussian with a mean that is given by the prior mean on the weights. So what we guessed the weights to be before we got to see the data, plus the covariance matrix of the weights with times the feature vector of the training data from the right. And then here's a big matrix that is the inner product between the feature vectors of the training data weighted by the prior covariance of the weights plus the measurement noise inverted times the observations, y, the data, minus what would be the prediction for these observations, the predictive mean, which is applying the features of the training data to the prior mean. So what's happening here is we're computing a prediction for what we think we're going to see. Then we see what we get to see. We take the difference between the two, that's the residual. We scale it by the predictive variance, so by what we thought the difference would be between these two, squared. And then so correct basically this measurement in this way. So that's kind of a scale on which we expect things to vary. And then we map back out onto the quantities we actually care about. So these are the observations and how we predict them to co-vary. And now the question is, how do these observations relate to what we care about? Well, they co-vary with the stuff we care about because they're related in a Gaussian fashion. What's the posterior variance on these weights? It's the prior covariance minus and then basically an outer product of these covariances between weights and data scaled by the inverse covariance of the data. So that's saying how much variance is in the data, so how informative is it to evaluate the data, and then scale from the left and the right, how they relate, how they covary with the stuff we actually care about. Now, as I pointed out in a previous lecture, it's possible to also write this very same expression in a different way using the matrix inversion lemma, which is maybe, at least in theory, due to Isai Schur, and we get another way of writing this resulting posterior weights. And actually, computationally, this is much better to do, because here we have a matrix that is of size number of data points by number of data points, so it's n by n, and we need to invert it, so the cost of that is going to be n cubed. While here we have matrices that are of size number of weights by number of weights, so this matrix is 2 by 2, and this is also 2 by 2. It's the same matrix, and inverting a 2 by 2 matrix is much easier than inverting an n by n matrix. To do so, of course, we need to get these quantities in here, in this matrix, and you can see that this is an inner product of feature vectors with themselves. So this operation is linear in the number of observations n. So doing this here is of cost number of features squared times number of observations. So f squared times n, f here is 2, so it's just 4 times n. Beautiful, so that's an easy thing to do, and then we only have to invert a 2 by 2 matrix. Okay, so once we have this posterior on the weights, we also get a posterior on the function values. And to get to that is actually a really straightforward operation. All we have to do is remember that the function f is actually just a linear map of the weights. So if you have a Gaussian posterior on the weights, given by this expression, or maybe this up here as well, then of course the posterior on the function values is given by just applying this feature function f of any input point you want to test from the left to the mean. So that's, you can see here, this is exactly this expression plugged in here again, and from the left we've just multiplied with the feature vector of any test points. And to get the covariance between two test points, we just multiply from the left and the right the expression up here, or actually the expression down here, with the corresponding feature vectors. So we're going to now look at how this actually works in practice for our concrete data set. However, at this point, it might be useful to you to just briefly stare at this expression and make sure you understood what we just did in this derivation. Now, not everyone likes looking at algebra in symbolic form. So if you're a kind of person who prefers to have a visual view on what's going on, let's do the same derivation essentially again, but now in a more visual form. So here is our prior distribution again that we've defined on a previous slide, a prior over the weights, which directly corresponds to a prior over the functions. I'll call this weight space and this function space. This is based on notions that come from the wonderful book by Carl Rasmussen and Chris Williams about Gaussian inference or Gaussian machine learning, essentially. Now we have this data set that consists of these measurements of, let's say, I mean, of course the data set is made up, but let's say this is a data set that is a measurement of torques or forces created by the motors in our robot, and we begin with our very first measurement. So you can already see the entire remaining data set plotted in here, but let's say we only get our very first data point so far. That's the first measurement we make. This one measurement is associated with a likelihood term that we multiply into our prior. This is a likelihood for this individual observation. That's a one-dimensional Gaussian distribution on this particular function space, but it's a linear map through the likelihood of these two weights. So in the space of these two weights, this Gaussian actually corresponds to a degenerate Gaussian, which is shown by this blue line here. That's the likelihood function. Now it's a degenerate Gaussian, so it has only a rank 1 covariance, even though it's a bivariate space. So you can see it sort of being, well, degenerate in this direction, but that doesn't matter. The product of two Gaussians is another Gaussian. And as long as the posterior has full rank, everything's fine. And because our prior Gaussian has a full symmetric, positive, definite covariance, even though the likelihood is degenerate, the posterior is still a full rank Gaussian. So the product of this green distribution with this blue distribution is this red distribution, which is our posterior distribution. You can see what the likelihood tells us. This one data point, written in terms of the weights, is telling us that the correct function probably has a positive slope because this point is below the 0. And it, according to this data point, it might not have an intercept. Actually, if it has an intercept, so this sort of, well, this likelihood actually says that the intercept could be anything, right? But if it's a positive intercept, then the function probably has to have a positive slope. And if it's a negative intercept, then the slope is probably a little bit less. So that means if the intercept, right, if the true function kind of goes through here, then it's probably a flatter function. And if the true function goes through here, then it's probably a steeper function according to this data point. And let's say we get a second data point in. Let's not just pick the next one in line, but maybe move to this one. This is a data point that is very close to the origin. So it provides relatively little information about the slope and actually not even all that much about the intercept, which is why we get a relatively wide likelihood here. So this is interesting maybe, even though this Gaussian and this Gaussian have the exact same width because it's measurement with the same measurement noise, the information content about the weights of these two data points is quite different. This data point is very close to the origin, and here the prior already is relatively narrow anyway, so this additional data point provides very little information, right? It just sort of cuts out a small part of the prior. So the product of this prior and these two likelihoods is now this posterior distribution, which is also corresponds to a posterior in function space, which is this red function. Now let's say we get one more datum that's up here. So what does this data point tell us? It tells us that the slope probably is positive because we're quite far above the prior width in this region. And therefore, the likelihood actually lies up here. See that you notice that the slope of this line here is now the other way around because we are on the right-hand side of 0. So what this likelihood says is this function probably has a positive intercept and a positive slope. If it doesn't have a positive intercept, then it has to be even steeper. So if the true line kind of goes through below here, then it has to be even steeper to go through this data point, which is why we go up here and vice versa. So now, of course, you can get many, many more data points. If we multiply all of our likelihoods in every individual datum, then we get an overlap of all these complicated Gaussian likelihoods. It's a bit of a busy plot now, obviously. And what you're left with is this small posterior distribution here, which is now quite narrow because it's a product of so many different Gaussian distributions that it actually has to be quite concentrated. And this corresponds to a posterior in function space, which you see over here, which is this relatively narrowly constrained region describing linear functions. You can still see the animated samples. So you can see that these red dots are also moving around just like the green ones. And we have contracted from this wide prior distribution to this narrow posterior distribution, which tells us quite a lot about what the true linear function is. We're not certain about what the linear function is, and in fact, given more and more of this data, we will never become infinitely certain. We'll just become more and more certain as the data accumulate about what the true function is. Okay, so this is what we're trying to achieve with these complicated computations. It's linear algebra that leads us to this conclusion. Here is this algebra again. It's a complicated expression, bunch of expressions. But now, if you wanted to implement this in code, you'd actually have to look at these expressions and get a feeling for how to implement them efficiently. So what I'd like to do now is save you that time and do it with you on screen in actual Python code. So what we're going to do is, and I'm not going to type it down, I'm just going to actually show you the code, is go through this process, which here is sort of nice curly symbolic mathematical symbols, and translate them into actual code. The takeaway I want you to get from this process is that Gaussian inference really boils down to explicit linear algebra operations, rather than a call to a complicated software library that is some kind of big black box that does something magic. So if you are a recent arrival to the machine learning world, then you might think of machine learning as this field that lives in these very complicated toolboxes like PyTorch or TensorFlow or what they are all called. And these are all complicated black box environments in which you have to use complicated stochastic optimization methods like stochastic gradient descent and ADAM and what they are all called. And somehow you have to just hope that this shaky construction of software will just work for you. By contrast, Gaussian inference consists of very elementary linear algebra operations. And for these, I mean, you still need certain toolboxes because you don't want to implement linear algebra from scratch yourself, but these are very low-level operations. So let's look at what this process looks like in code. And just to remind you, we're going to define a prior distribution on weights. We're going to define a feature function phi. These together define a prior distribution on function space. Then we're going to get data that we observe with a Gaussian likelihood, and we can use this data together with the prior to construct this Gaussian posterior on the weights and therefore also on the functions. And to do that, we just have to compute these quantities here, because Gaussians are entirely described by these two parameters, by the mean and the covariance. And to compute these quantities, we need to do a little bit of linear algebra. We need to take vectors, subtract other vectors from them, solve linear systems of equations. So this is not quite the same as inverting a matrix, but it's related to it. And then map again the solution of these linear problems through other vectors and matrices. So here's the code. I have deliberately written, I should say, this in a way that is didactically written. It's the most efficient way to do, or it's not the most beautiful Python code maybe. In particular, I'm going to show you scripts that do this computation. In practice, of course, you would implement this either in a more functional or a more object-oriented way with methods that allow you to swap out certain parts of this model. I'm not doing this here because I want you to see how simple the structure is really of this computation. So in particular, we are not going to load up here anything complicated like TensorFlow or PyTorch or whatever else. We are going to use NumPy, which provides basic linear algebra operations. And in particular, we're going to need three important parts in our process. Well, we need I/O because we need to get data in, fine. Then we're going to draw from a Gaussian distribution. For that, I load multivariate normal, which is a way to produce random numbers. Actually, in the flipped classroom, we'll talk in more detail what exactly this algorithm does, this little black box here, how it draws its random numbers, because it's a fun story of its own. And then we're going to do linear algebra, which NumPy mostly provides. And we're going to need one specific kind of linear algebra operation, which is to pre-compute efficient decompositions of matrices, in particular symmetric positive definite matrices, such that we can then afterwards essentially multiply with inverse matrices, which is not something you do in practice. Instead, we are solving linear systems using this operation, and these methods here are called Cholesky decompositions. Now, let's go back briefly to our math. What we are going to need is a prior distribution over the weights and a feature function to construct from this prior over the weights a prior over the functions. So what I'm doing in the code is I begin with the feature functions. They are here. So for this, I define the function that we've called phi, which returns our feature vector that is a 1 and x, or in this case, because the input is called a, 1 and a. And so here's one perhaps convoluted way of implementing such a function. Of course, you could also just write a function that produces a NumPy array that contains a and 1. I do this in this way because then it more nicely vectorizes, and we'll see later on that we can easily extend it. So what this produces is it takes in a, and then it computes the 0th power of a and the 1st power of a, because NumPy, or because Python is 0-based. This weirdly means that we take the power of a to the range of 2, which is the range of 0 and 1. And okay, that's our feature function. That was pretty straightforward. Now we need to have our prior. And for this, prior for the weights. And for this, I have the code here. So you can look at this later on Ilias, of course. I'll upload it. So here is the entire code on one in one cell. I hope that you can read this on YouTube. You might otherwise have to open the Jupyter Notebook directly. On YouTube, you might have to increase the resolution to see this. So this code consists of exactly the process that we've written in algebra before. We first need to define our prior on the weights. This happens in these 4 lines or 3 lines. Then define the corresponding prior on the function space. That's this part. Then load the data, construct the posterior, and that's the final bit. So first let's define the prior. For that I need a constant. I need to know how many features my feature function actually returns. That's called f. For that I just evaluate the feature at any particular input point. Let's take the 0, it doesn't matter, and just check how many entries there are. And now I know that I need 2 features essentially, or weights for 2 features, so 2 feature weights. For that we need a mean vector and a covariance matrix. As in the examples I've shown you before, I'm going to set the mean vector to 0 and the covariance matrix to the unit matrix. That's what's happening here. Okay, that was easy. Now we have our prior on the weights. What's the corresponding prior on the functions? So notice that, of course, a function is a more abstract object. I could implement this in a more functional style, actually producing functions that can be evaluated anywhere. Now, I've noticed in the past that it's often easier for people to understand if we talk about a concrete realization of a function. Now, a function is something you actually evaluate at some point. So what we're going to do later on in this course, in this Jupyter Notebook, is we're just going to actually create a plot. So how do you make a plot? Well, you need a plotting grid. And here I'm creating this grid. I'll say we'll take 100 points and distribute them evenly from -8 to 8 so that we can make a nice little plot. And now let's compute the prior distribution on the function values of those 100 points. Because that's actually how I made these plots that I've seen on the slide so far. Maybe if you want to play with this code, I'll leave it to you to think of a more functional form for this that leaves the feature functions as functions themselves and then only evaluates them more lazily when they're actually necessary to evaluate. So what is the mean vector for the function values at all these 100 locations? Well, it's the inner product between the feature vector and the prior mean for the weights. That's this thing here. And what's the covariance of these functions, function values? Well, it's the inner product from the left and the right of the feature functions weighted by the prior covariance sigma. So notice that in this code I've actually defined phi to be a row vector rather than a column vector, so the transpose is on the other side. Doesn't really matter, right? You just have to take care that everything fits together. One beautiful thing of linear algebra is that if you are ever so slightly careful, then the linear algebra actually does some kind of implicit type checking for you by making sure that the matrices fit to each other when you evaluate them. Now we have the prior distribution over the weights, over the function values. It has a mean and a covariance matrix. And what we can do with it is, well, we can draw random numbers from this Gaussian distribution and we can make plots. For the plot, we actually need this sausage of uncertainty around the function values that you've seen on previous slides. I'll show it to you again so that you know what I mean. It's this green region here, this line. This line is the diagonal of the covariance matrix. In fact, it's the square root of the diagonal because it's a standard deviation. So let's get this diagonal from here. We just extract it from the covariance matrix. Then we take its square root and do a little bit of numpy foo to make sure everything works. That's something we can plot later on. We can also draw random numbers, these lines that I showed in an animated fashion on the previous slides. I'm not going to create the kind of samples you need for animations. That's sort of some advanced question. We can talk about that in the flipped classroom if you like. Just bring it up. So to do that, I just tell NumPy to create random numbers from a Gaussian distribution with the mean given by m and a covariance given by kxx. And please draw 5 of these because then we can make a nice plot. Okay, now that was the prior. Now we load data. So for that we do some I/O. I actually have this data lying around in some MATLAB format, but of course it doesn't matter. I just load it from somewhere. And then now we have the data. So the data it's a supervised problem. So data contains x's and y's. And also it comes together with a noise. So with sigma. Sigma is the standard deviation of the measurement noise. Notice how this parameter sigma is actually part of the data set. This is a typical situation. So if you're an engineer, right, you take your measurements of how much force your motors are producing, and then you look up on whatever device you're using to measure the force or the torque. You turn it around. Somewhere on the back there's a piece of paper glued to it that says measurement precision plus minus whatever so and so many Newton, and that's exactly the sigma you plug in here. Providing the error is part of the model and part of the modeling task. So if you know what the error is, and maybe you do, then you have to plug it into the likelihood. Now we also need to know how many data points there are, so let's just figure out how many entries X has, and let's call that capital N. Now we have data, and now we can do inference, or learning if you like. So to do that, we need the quantities that show up in these equations on this slide. So we need this matrix here, which is the inner product between the features of the data and itself, weighted by the prior covariance, plus the noise. And then in the symbolic form here, we wrote the inverse of that matrix times a vector. Now, we are going to need the inverse of that matrix actually twice in this computation. Actually, so now there are two issues with linear algebra on a computer. The first one is that it's usually the wrong idea to actually compute the inverse of a matrix, because matrix inversion is a numerically complicated process that is also relatively inefficient. There are smarter ways to do this process because we don't actually need this matrix. We only need this matrix applied to a vector. So to do so, we should solve a linear system of equations, which is actually a more well-behaved process. And secondly, we have to keep in mind that we have to do this twice, here and here. So we should pre-compute the complicated part of this operation and then leave the simple part, which is applying this object to this vector, to later steps. And to do so, I am going to decompose this matrix into an upper triangular matrix called the Cholesky decomposition, which always exists for these symmetric positive definite matrices and which can be computed in cubic time relatively efficiently and numerically in a stable way. And then once you have this upper triangular matrix, you can apply it efficiently by back substitution to both of these problems and efficiently solve this linear system. So let's do that. So we first compute this matrix. It's called phi transpose sigma phi. And we need this prior mean. That's this object, sorry, the prior mean on the data. That's the object we're going to subtract from the data to get the residual. And now we compute the prior covariance of the data. The prior covariance of the data is the prior covariance of the latent function plus the variance of the data. And that's just how the math works out, as you could see on previous slides. Now we do the complicated computation. That's this line here, which is by far the most expensive bit of this entire cell. This pre-computes the Cholesky decomposition of this matrix. So it computes an upper triangular matrix, which you can then use for efficiently solving several linear systems. And then once we have that factor, we can apply from the right or from the left this object, which is this k little x capital X, which is the inner product between the feature functions of the test point or the predict point, the point where we are going to evaluate the function, the covariance of the weights under the prior, and the features of the data. Once we have that, we can compute, let's go back to our math. Once we have that, so I've actually computed this object here, that's the phi k little x capital X. And what we're now going to do is actually to produce posterior predictions on the functions rather than the weights. We're going to take the data, subtract the prior mean on the data that we just computed, solve this linear problem, and apply from the left-hand side this k little x capital X, and maybe also add the mean. In this case, we don't have to do that because the prior mean was 0, so this part is just 0. Okay, so to do so, we get, we compute a posterior mean, here we go, which is the prior mean plus, which happens to be 0, plus A, which is the solution of the linear problem that is given by G inverse times K little x capital X. So let's go back. That's this part here. That's this entire expression, including this bit outside of the matrix. And then multiply it from the right with y minus mean. And you see that over here. Then you get a posterior covariance, which is given by the prior covariance minus kxx times G inverse times kxx transpose. And that's exactly what we're computing here. We're just reusing the matrix inverse, or the work we put into producing a decomposition of a matrix which makes matrix inversion implicitly efficient to compute the posterior covariance. Once we have these two parameters of the posterior distribution, mean and variance, we can now, for example, draw random numbers from it using, again, the multivariate normal formalism with a mean and a covariance. Let's draw 5 samples. Or we can plot this posterior sausage of uncertainty by extracting the diagonal from this covariance matrix, taking its square root, and use that for plotting. Now, if you go further down, like on Ilias, if you look at this code and go a little bit further down, you'll find the code for creating the plots as well, but that's just somewhat tedious. Actually, I can go down here. It's just a somewhat tedious bit of matplotlib foo. So this produces these plots, and what it does is it just reuses all the quantities we just computed and makes nice shiny pictures out of them. Other than that, that's all. So the important bit to take away here is that this is all just linear algebra. It's all elementary operations you can do with NumPy. It's no calls to complicated software packages other than standard linear algebra libraries. But I mean, these have been around for 50 years or so, so they are not a particularly new invention. This is important because it shows how elementary Gaussian computations are. They are totally understandable. They are well structured. They are numerically very efficient. And running this piece of code takes much less than a second for this data set. All right. So with this, we are actually at a good point for you to maybe take a break and briefly think about what we've done. We've constructed a framework for inferring a function, learning a function. Of course, that's a core operation of machine learning, a supervised learning problem. We have seen how to solve such a, admittedly, basic form of supervised learning problem using Gaussian inference as a mechanism to map the abstract notion of probabilistic inference onto linear algebra. Once you've taken your quick break, we can go on to ask the obvious next question, which has been probably on your mind for the past few minutes already, which is, but what happens if my dataset looks like this? Now, of course, in practice, very few functions are actually linear. And if you really have a linear straight line function to learn, maybe you don't need to break out the complicated probabilistic machine learning toolbox, and you can use some simple old idea. I mean, in fact, actually, many of the things we talk about here are old ideas, to be honest. They are sometimes several hundred years old. Gauss himself, in his original work on the orbits of planets, essentially solved exactly this problem. He made observations of the planets at various points in time and then fitted a function that amounts to a posterior of a Gaussian distribution. We'll talk more about this actually later on a little bit. So let's say your robot doesn't work in this simple way. It has a more complicated, it exhibits a more complicated relationship between X and Y. Maybe this is the data that you've actually collected. Now you can tell, of course, that there is no straight line that goes to this data that explains all this data well. However, the situation is extremely similar to before, right? We still have an input and an output. They're actually still of the same type. They're both real valued in this simple example. There's still a latent function f. It's just that this particular linear form, that f of x is just one constant plus another constant times x, doesn't fit anymore. So the question you can ask yourself is, what do we need to change in our framework to make everything work? Well, do we have to change the Gaussian inference bit? This is an important question to think about. Remember again which properties of Gaussian distributions we used to make all of this work. We used the fact that Gaussians are closed under linear maps. That's the important part. Now, the way we use that is by constructing a linear function, but a function that is linear actually in two different ways. The function we looked at, f of x, happened to be a linear function in x, but it was also a linear function in w, because we can write it this way as well. Now, the bit that we actually used to make inference easy was not the fact that the function was linear in x. It was the fact that it was linear in w. So think for yourself, what could you do now that your data set looks like this to create another kind of model that can deal with this kind of nonlinear shape? Normally in a lecture, I would ask for questions, like for answers from the audience. You might want to stop the video here for a few seconds and just think about what you can change. So maybe your answer was, and that's usually the answer that comes up, to say, well, maybe we could just change the features. There is not really a reason why we only needed a constant and a linear feature. We could add more polynomial terms here. We could go to quadratic or cubic terms, right? What do we have to do to make this work? Actually, let me just first show you a picture. Here's what this looks like. Instead of just using a linear feature, instead of just using a constant and a linear function, I'm going to use also a quadratic and a cubic feature. So that means I'm assuming that the function we're looking for is a cubic polynomial in w, in x, right? And linear in w. So there's now 4 unknown numbers: the weight for the constant term, the weight for the linear term, the weight for the quadratic term, and the cubic term. So I can't show you a picture of the weight space anymore because it's now 4-dimensional. But I can show you the picture of the corresponding prior over the function space. And you can see here wobbling around in this picture various polynomials of 4th order. And you can see that the hypothesis space now looks a bit more different. It's more non-linearly shaped. And if you compute the corresponding posterior over this cubic function, then this is actually what you'll get out. It's a non-linear function. You can't really see that this is a cubic function, but it is. So the important bit is, what did we need to change in our code to make this work? And for this, let's go back to our Python notebook. Do we need to change anything in this code? You might want to stop the video and think about it for a moment. The answer is no. This cell stays exactly as it is because the only thing we changed is the features, and the features are defined up here. So now you might realize why I chose to write our feature functions in this way, because all I have to do to get to a cubic function is to change this 2 into a 4. That's it. Nothing else changes. The entire remaining code just stays the same, and we get this kind of output. Now, actually, this isn't a particularly good model for this data set, and you can see that it's not a good model because the data is not explained well at all by this model. The probability of getting to see this data under this model is very low. Now, think for yourself, where does this probability for the data to be produced by this model actually show up in our Bayesian inference? It shows up in the evidence term, in P of y, in the denominator of Bayes' theorem. And we can compute that because it also takes a Gaussian form. If you would do that, you would see that it's actually extremely unlikely that this model produces this data. But the Gaussian framework doesn't really, well, the Gaussian framework provides a way, but the Gaussian posterior doesn't really adapt to this. As you can see, the uncertainty of this model is very low in this region, even though the data is quite far away from the prediction. This is an important aspect of Gaussian inference, which is caused by the fact, if you like, that the posterior is given by this expression. Here's the posterior over the functions, here's the posterior over the weights, written in various forms. What you can notice is, let's say we look at the posterior over the functions. That's maybe fun to look at. Here, and let's look at this line, at this form. So here's the posterior mean, and here's the posterior covariance. Now notice that the data that we see, y, actually only shows up in the mean. There is no y in the posterior covariance. And this means that the posterior uncertainty doesn't actually depend on the numbers you got to see, right? And that's why we get this overly confident region here. The Gaussian framework, at least in the way that we've used it so far, does not take into account or does not adapt to data that is actually badly fitted by the model. So what do we need to do to address this issue? What do we need to fix to make this work? Maybe your answer is, okay, maybe let's just use more polynomials, right? So third order is maybe just not enough to get this wiggly shape. So let's use 7 terms or 8 terms, right, up to 7th order polynomials. Then this corresponds to this more complicated model, which is more adaptive, and it learns this kind of function. Again, think for yourself, what do we have to change in our code to get to this point? Well, we just have to replace a 4 with an 8. Nothing else changes. Okay, this is what the posterior now looks like. Well, maybe this is still relatively dissatisfying for you because the data is still not perfectly described, but perhaps more worryingly, you get this extreme divergent behavior on both ends of the data set. So maybe this isn't the right thing to do yet. So what else could we do? Think of various other ways we could do to fix this issue. Now, normally here in a lecture, it takes a few seconds for people to realize that there is nothing in the definition of this code so far that requires us to use features which are polynomials of x. And in fact, any other function of x can work as features. And then I often ask people, so what are the features you would like to use? This is actually my favorite part of this lecture, and it's so annoying that you're not here to share this moment with me. And then people usually say, you could use oscillating functions. Oh, you could use Fourier features like cosines and sines, and let's use that, right? So here I've used a feature function which provides, which takes in x, and then it returns the cosine of x, the cosine of 2x, of 3x, and so on until 8x, and then the sine of x and sine 2 of x until the sine of 8 of x. You can see the feature functions in this plot. There are these blue lines here. These are all the cosines and these are all the sines. There are 8 of them each. Again, what did I need to do to make this code work? Well, I needed, let's go back to our Python code. I don't need to change anything down here. All of this stays exactly the same. There's no change here. The only thing that needs to change is this cell. And in fact, one of these cells, I don't really know which one, is the one that we're going to use. Let's see, it's, there's a bunch of features. This one here, sines and cosines, which we use for this particular plot. So if you use these particular feature sets, then the posterior looks like this. Now, okay, that's still not great. It's a little bit smooth here in this region. So the reason for this is that I've actually not used features of sufficiently high frequency. I'll leave it to yourself to play with the code that I have on this Jupyter notebook and change the frequency so that you fit a little bit better in this region. You can think for yourself about, because we are at 0 here, whether it's better to change the sine or the cosine features for this particular data set. So one nice thing about this posterior is that it's much more well behaved in extrapolation. It's kind of much more smooth. It doesn't diverge in this extreme fashion as the polynomials did before. It's also maybe perhaps not so perfect because one assumption that is encoded in these features is that this function is periodic. So if we would extend this plot to the left or the right much further, you would see this function start to oscillate back and forth. Maybe that's not what you want. Maybe you know about something about your data that is periodic in this way, maybe you don't. And depending on whether you know that or not, you might want to include this as a feature set or not. So normally at this point I say, okay, are you happy with cosine and sine features? What other features might you want to use? And I very much encourage you to do this for yourself. Stop the video here, think for yourself about the kind of features you might want to use to model this data set. So then one next idea people often come up with is pixels. So if you come from a computer vision graphics kind of background, then maybe pixels are a very natural thing for you. So what you could use is little steppy functions, right? That to describe your function space so that you have a lot of flexibility because step functions allow big jumps in data points from one point to the next. So there's a bit of a technical issue actually when I say I'm going to use step functions, we need to say exactly what kind of step functions we need because there are 2 different step functions. There are step functions, actually there are 3 different step functions if you like, right? As one kind of step function is this one. So these are step functions that start at -1 and then they move up to +1 at some point. And each function moves at a different point. So here, this set of step functions starts at, well, here's the first one that moves down from +1 to -1, and here's the next one from +1 to -1, +1 to -1, and so on. There's a little bit of a slope in these lines. That's just a plotting artifact. They are actually hard steps, discontinuous steps. And every single one of them can be switched on independent of each other. But because they are all non-zero everywhere, they're either plus or -1, they all overlap with each other. And you get this kind of hypothesis space that can create really steppy, blocky functions. And if you apply this to this data set, this is the posterior you get. So, okay, maybe this looks a bit ugly, and you might find this a bit annoying, right, that it has these hard steps. But in many ways, this is a very flexible modeling class because it allows very strong steps in the function and can adapt to them without getting having nasty effects elsewhere in the predictive range. And it also extrapolates kind of nicely. I mean, of course, there are these steps, but towards the left and the right here, you just get relatively flat behavior, like non-nasty extrapolatory behavior of this model. Maybe this is not so bad. Actually, there's another kind of step functions, which are the step functions that start at 0 and then switch on at one point. So here I use this Heaviside function notation, which just a function that is 0 if its input is less than 0 and 1 once the input becomes positive. So if you have such a model, then here on the left-hand side, all the features are 0, and therefore the hypothesis space for function values also ensures that all functions must be 0 over here. And then as we move along to the right, more and more of these features switch on, and they all add up together, and so there's more and more room for function values to grow. These kind of technical issues in the definition of the features actually matter then, right? They directly affect the hypothesis space created by this. If you don't know why I belabor this so much, then maybe keep it in mind if at some point we start talking about deep learning again, and maybe you've already thought about deep learning before, and you might understand that the choices of features are actually really important, and that this way of thinking about regression in a probabilistic fashion produces, gives you an intuition for what's going on that is much harder to create with deep neural networks. So, okay, this is our hypothesis space. Now, if we get data and adapt the model to the data to compute a posterior, this is what the posterior looks like. Now, notice that on the left-hand side, this model has to return to 0. It has to because there are just no features over here to explain anything other than 0. And it adapts sort of around here to the data. Now, at this point, I again ask people, what other models can you think of? And then they usually come up with all sorts of other ideas. We can do a few here, and I very much encourage you to download the code and play around with it yourself and see what else you can implement. So here is, for example, a bunch of features that are little v functions. So they come down from the left, and then they go back up to the right again. And they are sort of shifted a little bit in a linear fashion so that, things get easy to implement. And they create this kind of hypothesis space of functions that are piecewise linear, because the features are piecewise linear. But they are sort of extrapolating in both directions. If you use this kind of prior, then you get this kind of posterior. This is actually quite nice, right? It looks like a good interpolation. It's very adaptive. And the functions we get are piecewise linear, so they are reasonably well behaved. They don't have these nasty steps anymore that we got from these pixel-like functions. You could use also all sorts of other kind of weird, maybe not necessarily nasty, but weird or maybe exotic choices of features. So in certain applications in science, people have come up with very smart choices of features. Here, for example, are Legendre polynomials, which are an interesting set of polynomials that are defined on a bounded domain. So maybe you know for some odd reason that your data explicitly lives in this domain from -8 to +8, and all the dynamics of the function are constrained within this region. Then you could use such a basis, and it would produce a very funny, nice, beautiful hypothesis space. And if you now adapt your model to compute a posterior, if you do learning or inference, which are all the same thing essentially, then this is the posterior you get out. Or maybe you could use what I call Eiffel Tower regression. So I'm not actually sure this is exactly true, but I've read somewhere that in log space the Eiffel Tower is a triangle. Maybe that's wrong. But if it's true, then it corresponds to this kind of feature set. So here, the phi of x are exponentials of absolute distances of x from centers, from various centers. And here I've varied these centers from -8 to +8. There are 16 of these features. You can see them in blue here, or maybe you can think of them as little Fuji mountains. Maybe that's a better way to explain this. Maybe I should call this Mount Fuji regression. This is the prior hypothesis space. You can see that the features create these little artifacts in the marginal variance. They kind of go up and down, up and down. And if you compute a posterior for this model, then we get this kind of output. Again, now you could complain about certain features of this model, but maybe you don't have to. Now at this point, usually someone raises their hand and says, but how about Gaussian features? And of course we can use these as well. I just do them at the very, very end because I don't want people to think that you can only do Gaussian regression with Gaussian features. So here are what people might call Gaussian features, or also sometimes they're called square exponential features or radial basis functions, because people don't want you to get confused with the Gaussian nature of the inference. So here the feature functions are exponentials of square distances. So these are essentially Gaussian functions. But notice, of course, just to remind you, that the entire framework here uses Gaussian inference, and it doesn't matter at all what the shape of these features are, right? It just happens that we now decided to use these smooth little bell-shapy functions. If we do that, then one nice aspect of this is that these functions become very smooth. So the green lines you see here animated, the draws from the prior, are always very smooth functions because they are sums of extremely smooth functions, of these Gaussian bell-shaped functions. If you use these, then the posterior distribution looks like this. And many people find this aesthetically pleasing. I mean, I agree, it's a beautiful plot that it kind of creates this kind of smooth lines that go through most of the data points because they just kind of get shifted around in the right way. And it extrapolates in this kind of fashion. Now, whether you like this plot or not depends on what kind of aspects you care about. Maybe you want to do extrapolation, and then this model is not particularly good in extrapolation. So if you go back one slide, you see that over here, actually, I've stopped adding features. So to the right and to the left, this model actually returns to 0. So if you extrapolate far out, then this model will just predict 0 values outside of this range. Maybe you like that, maybe you don't, right? Maybe you care about the interpolation at this point, and then you notice you might be happy about the fact that this is a very, very smooth function that interpolates beautifully between the data points. Now, the question at this point that is probably in the back of your mind if you are an analytic person is, okay, now I've seen 8 different features. What kind of features am I allowed to use? So here's the question to you. What is the set of feature functions we are allowed to use in this framework to do regression on a real valued function? And the answer is, there is no constraint to this feature set for all intents and purposes. Sometimes people then say, oh, but what about discontinuous features? Am I allowed to use discontinuous features? And the answer is, of course you are allowed to use discontinuous features. Let me give you an example. Here are functions that are discontinuous. They have hard steps from 0 to 1, and it's totally fine. It's not a problem at all. There is really no constraint on the feature functions. All you need is a function that maps from x to the real line, and then you can do that. By the way, this of course means that x doesn't have to be a real number. So we could come up with features that map, let's say, from a bivariate space, so from a 2-dimensional real input space, x1 and x2, to the real line. So here for this example, I've created a little egg carton of features. So I've created these bell-shaped square exponential features and tiled the space with these kind of features. So there's quite a lot of them now. There's, I think, 10 or 8 in each direction. So this is 64 of these features. All we need is a function that maps from x to the real line. If x is a bivariate real valued input, fine. Then we get a hypothesis space over multivariate functions. And of course, x doesn't just have to be 2-dimensional. It could also be 100-dimensional or 10,000-dimensional or million-dimensional. This doesn't really change anything about the process, because if we go back again to our code, think again about where x actually shows up in this computation. Actually, it doesn't show up at all, essentially. I mean, it does show up here as an input to x, but when we compute our mean and prior covariance, x is already shielded within phi. So beyond this point here, and where the data comes in, we never actually use x explicitly. We always evaluate the features of x and then operate on the space that is spanned by the features of x. So in fact, x could be multivariate, but it could also be something more exotic. We'll talk about other models later on where x is maybe a string or a graph or anything else. It could be an image, and images are essentially multivariate vectors, right? But it could also, just to drive home that point, actually be a one-dimensional input, but then we could map to a multivariate output. So, for example, we could say our input space is one-dimensional. Here we have time. So x is now just time, basically. And we have, let's say we have two different outputs. We have an output which we might call x and an output which we might call y. Now, we could take our time t and just produce two sets of features. Every point in time is associated with two features, one that affects y and one that affects x. Then, since we are just learning weights for these features, these two-dimensional features together span a two-dimensional space across time. So here's this three-dimensional space, and if I draw from this Gaussian prior over the weights of all of these features, we are essentially producing this three-dimensional object. Now, if you look at it from above, like if you turn this cube and turn it around, then you see a curve. So of course we can use Gaussian regression not just to learn nonlinear functions from x to y, but also to learn curves rather than just functions that map from x to y, as long as we know where in time we are evaluating these curves. So I'm showing you all of this partly as a sales pitch for this beautiful framework to do regression on functions, which we're going to be discussing for several lectures from now on, but also to maybe create a bit of a worry in the back of your mind, which is maybe phrased well in the following way. So what we've just discovered here is that we can use any feature set to span a space of hypotheses of functions which we might want to learn. And if we change the feature set, then we get very different kind of priors over function spaces. Function spaces like this, or like this, or like this. And these are all clearly very, very different. Now, maybe that's a good thing, because it means you are free to design a very powerful model for your inference task. Maybe this is a problem, because it means that you are forced to design a very specific hypothesis space for your inference task. So in future lectures, we'll have to think about how to deal with this worry and how to come up with ways of adapting these features for us, or somehow other ways of dealing with this having to choose features. But for today, I'd like to end here and summarize what we've done. Today, for the first time, we got to the point of doing a basic form of machine learning. We noticed that Gaussian distributions, which map probabilistic inference to linear algebra, can be used to learn not just individual numbers, but actually functions. And we do that by describing the function space in terms of a finite number of numbers. And then match or connect these numbers to functions by writing the function as a linear map from the weights into some other space, but that other space is spanned by features over the inputs x. Doing so allows us to learn even nonlinear functions of the input as long as they are linear functions of these latent weights w. Such models are sometimes called general linear models, and we'll talk more about them in later lectures. What we saw is that the choice of features we can use for this. So first of all, we saw that implementing these methods is, let's say, easy because it doesn't require complicated software tools. It just requires linear algebra. It's also fast because it doesn't require nonlinear optimization, stochastic optimization, and so on. It can typically be done using just linear algebra, which is a particularly efficient operation on a computer. And then we discovered that we can use a very rich set of features to create nonlinear hypothesis spaces over functions. And this is maybe beautiful because it allows, first of all, it should just be seen as beautiful because it allows you to create very specific, very powerful hypothesis spaces of functions. And in many applications, maybe you actually know enough about the function you're looking for to be able to design such explicit features, which then allow you to actually learn structure from your data. And we're going to do more examples of this in later lectures where we actually do this kind of very structured inference. Of course, it also maybe raises the worry that having to do this, having to design features, is perhaps not ideal. And if you want to have a generic learning algorithm, you might want to have a way of dealing with this issue that you have to choose features. We'll talk about how to do this and actually several different ways of dealing with this issue in subsequent lectures. I'm hoping to see you there again. Thank you very much for your time.